So in this lecture, I'd like to focus on an assumption that we made in the analysis of the BB84 protocol, which is the assumption that Alice and Bob have access to authenticated public channel. I want to discuss a little bit whether this is a reasonable assumption or not. So if you remember what the BB84 protocol is, it involves Alice sending BB84 states to Bob, and then it has some pretty lengthy phases of public communication. So for instance, Alice has to choose some bases and obtain some outcomes, and some of these bases are exchanged between Alice and Bob. Also, some of the bits that are outputs are exchanged, not all, but some of them. And then there's some more discussion that's going on when you perform information reconciliation, and a little bit more information that's exchanged when you perform privacy amplification. And one of the assumptions that we made is that the information that's exchanged on this channel is public, meaning Eve has access to it, but it's authenticated in the sense that it cannot be corrupted by Eve. So Alice, when she receives a message, has the guarantee that the message has been sent by Bob, and it's not a fake message that was created by Eve. If we allowed Eve to corrupt the messages, she could potentially mess up the whole protocol. She could intercept all these bases and these bits and all this information, as she can do in the version that we've analyzed so far, but she could also modify them and tell Bob some bases that are not the bases choices that were made by Alice. In that case, the protocol would be completely insecure. So this authentication is an important assumption for our protocol to be secure. And the question is, how do you establish an authenticated channel? So let me tell you how this can be done. The main idea is to use a cryptographic primitive that's a completely classical primitive called the message authentication code. So what's a message authentication code? It has three parts. The first part is a key generation procedure. So K here is called the key. The input to that procedure is just a length parameter n. This n is called the security parameter. The bigger the n, the more secure the authentication code will be. Once you have a key, there's two different procedures. The first procedure takes as input the key and the message m, and it produces a signature or a tag of that message. This is supposed to authenticate the message. And then the other procedure is a verification procedure. It takes as input the same key k, a message m, a purported tag for that message, and it outputs accept or reject. The idea being that if the tag is a valid tag, if sigma is tag k of m, then it should accept, and if it is not, then it should reject. That's the correctness requirement for message authentication code. So now what's security of a message authentication code? Well, we'll say that the MAC is secure if no adversary, and what is the adversary given access to? The adversary doesn't have access to the key, but what it has access to a certain number of message tag pairs. These are things that it could have learned by listening in on a communication channel. So the adversary sees a bunch of m sigma pairs that are valid, but we'll say that the MAC is secure even though the adversary has seen all these message tag pairs. It is not able to come up with a new message that it hasn't seen so far, let's call it m prime, and a tag sigma prime for that message that will be accepted by the verification procedure, right? So that's security of a MAC. Given many message tag pairs, you are not able to come up with a new message and a valid tag for that message. So if we have such a thing, you see how you can use it in order to authenticate a public channel. What Alice will do simply is that instead of sending directly her basis information, her output information, she'll send the same information, but tags for that information. And when Bob receives it, he'll verify that the tags are correct. Now, of course, in order for Alice and Bob to implement the tagging and the verification scheme, they need to share the key K. They need to share the same secret key, which is exactly what they're trying to achieve when they're doing quantum key distribution. They're trying to come up with a key. So the assumption that they have access to an authenticated channel actually requires them to share a key a priori. And so the question is, how long does the key that they need to be in order to implement the message authentication code. So let's see one simple construction of a MAC. And in fact, it's possible to construct MACs using a primitive that we've already seen, which are two universal families of hash functions. So I gave the definition for you here again. A family of hash functions from n bits to m bits is two universal if the probability over the choice of a random hash function that the hash function maps two different inputs, x and x prime, to certain arbitrary strings, z and z prime, is the same probability as you would get 2 to the minus 2m simply by choosing uniformly random outputs for the values of this hash function on x and x prime. So now suppose that you have such a family of two universal hash functions. Here how you could create a message authentication code out of it. What the key generation procedure will do is simply output the label of one of these hash functions. Now the tagging procedure, given the label of the hash function and a message, which I'll think is just an n-bit string, will output as tag the value of the hash function evaluated at the message. And what the verification procedure will do is it'll simply do the same computation, evaluate the hash function on the message, and check that the signature is equal to this. Now if you think through the security definition that I gave you on the previous slide, you can show that this MAC has the property of being so-called one-time secure. What being one-time secure means is that if you're given one valid message signature pair, then the probability that the adversary can output another valid message signature pair, where m prime is different from m, then this probability will be at most, in our case, 2 to the minus m. You can show this simply using the property of true universality of the family of hash functions. So this works. Then what you could do is that every time Alice wants to authenticate a set of bases or a set of outputs, she chooses a hash function at random from a family of two universal hash functions and uses that to authenticate her message. Now we've seen constructions of two universal families of hash functions, and we've seen that the size of such families is typically 2 to the 2n, where n is the size of the input, which means that to choose one random function from that family, you had to choose this a and b, the coefficients of the hash function, as an affine function. So you need 2n bits, which means that using this MAC, you need 2n bits of private key in order to authenticate n bits of message. Now that's not quite good, right? Because the protocol, BB84 protocol, exchanges many more bits than the bits of key that are produced in the end, which means that you actually need more bits of key than you are producing using the protocol. So that's not good at all. You have to do something better, and in fact it turns out, using more elaborate constructions that I'm not going to discuss in this video, that you can do a little bit better. What you can do is that you can achieve the same with roughly log 1 by epsilon bits of key, where epsilon is your security parameter. So that's the security of the MAC, independently of the number of messages that you want to be able to tag. So this is pretty good. You can do with a fairly short initial secret key, and as long as that key is about the length of the security that you want to achieve in the end, then you'll be able to use it and reuse it as many times as you want to authenticate all the messages that are exchanged in the BB84 protocol. But still, you need to have a secret key to start with, and so this is a limitation that I wanted to make you aware of, because it's a limitation of all the key distribution protocols that we know. You need a little bit of private key to get started. Now, why is this not too strong an assumption? First, there's the case that this key doesn't need to be too long, and then you can also make another argument, which is the following. The argument is that the bits of key that are produced in the BB84 protocol have this property called everlasting security. And what everlasting security means is that once the key has been produced, even if the authenticated channel that was used in the process of coming up with these bits is broken, even if its security is later compromised, the bits of key that have been obtained at the end of the protocol are still secure. Why is this the case? Well, because if an adversary breaks the authentication channel, sometimes after the protocol has been executed, then what is the adversary going to do with that information? Anyways, we already assumed that anything that was exchanged in the authenticated channel was public, so the adversary has access to it. So if it is able to break the authenticated channel in the time that the protocol is being executed, then that's a problem. But if it breaks it later on, then that's not a problem at all. Which means that we can consider implementing this authenticated channel not using information theoretic security, as I showed you could be done in the previous slides, but you could also imagine using an authenticated channel that's secure under computational assumptions, under the assumption that the adversary has limited computational power. In that case, you do not need any private key to start with, but you are making this computational assumption. On the other hand, because of this property of everlasting security, you only need the computational assumption to hold for the lifetime of the protocol. And there it's reasonable to say that even if the adversary has quite some amount of computing power, it's not going to be able to break the authenticated channel just in the lifetime of the protocol. This protocol is going to be executed rather quickly, maybe it'll take just a few minutes. And so we're making the assumption that the authenticated channel can remain secure for just a few minutes. That's a fairly weak assumption. It seems reasonable. If we're willing to make that assumption under computational assumptions, then we do not need any private shared key to start with, and quantum key distribution lets us achieve a secret key with everlasting security, or so-called everlasting security, based on no assumption except aside from this computational assumption that needs to hold for the lifetime of the protocol.